possibly even more intense than yesterday, because we're going to start quite abstract, so answering the question that we asked yesterday. So how can a total derivative in the Lagrangian density have a physical effect? Then we're going to move on to something a bit less technical and rooted in quantum field theory. So we are going to talk about a phenomenological problem of the axion solution to the strong CP problem. Then we'll keep going, moving in a more and more fino direction and talk about dark matter axions. And finally, dark matter, and finally axion dark matter experiments. From a theorist perspective. Well, hopefully we'll have time to cover all this. Let's try. So, okay, the first question. So as I promised you yesterday, you can write this term as a total derivative. And I leave you the derivation as an exercise. So why do we say that the total derivatives don't have a physical effect? Well, so if you integrate this object, so this divergence, you're going to get a surface integral now. So you're going to be left with an object that looks like this. And so if k for r to infinity is bounded by 1 over r cube, or decreases faster than 1 over r cube, this object is going to 0. Okay? Now, why do we expect it to decrease faster than 1 over r cube? Well, one way to see it is just that we're always thinking about systems at finite energy. So if, for example, we define an electric field in analogy to electromagnetism, so from the field strength, and similarly we define a magnetic field, then, okay, we can write the total energy, if we're looking only at gluons, as something like this. Where a sum over the color indices is implied. And so if you want this quantity to be finite, you need the absolute values of the two fields to be bounded by 1 over r squared when r goes to infinity. And since we can write our GG dual as the scalar product of the electric and magnetic fields, then, well, from this and the relation with k, so the fact that this is also a derivative of k, we can conclude that k at infinity is bounded by 1 over r cube. So naively, we would say that for this reason, our CP term in the QCD Lagrangian should have no observable effect. However, well, there is an exception to this argument. So we might ask if there are field configurations that don't decrease that fast at infinity, but still maintain the energy finite. And the simplest option is if at large distances our gauge fields become pure gauge. Where U is an SU3 gauge transformation, so an SU3 color gauge transformation. So it requires some work, but on this configuration, the gluon field strength vanishes. So if you compute it for something that is pure gauge, let me call it G. Okay, so also these contributions to the total energy goes to 0 at infinity if the field goes to this pure gauge configuration. So we might hope to find functions, so gauge fields, that do not decrease this fast, but still leave us with a finite energy, okay, because of this mathematical property of configurations that are pure gauge. So, okay, at this point, we could just look for a solution of the equation of motion that has this property. And if we are as smart as Toft, we might even find it. So one example is the following. So is if the gauge field looks like this. This is just one possible solution, and it's known as an instanton. And this rho parameter is a free parameter that we have to integrate over to consider, I mean, for this to be a solution. So, okay. Fine, we just went through these steps, found this solution, but the question remains, so why is this solution relevant to us? So why would we want to expand the path integral around this solution? Normally, what we do is to find the ground state of the theory, the minimum of the energy, and then we quantize fluctuations around this minimum, and that's what we call our quantum fields. But for now, we just found a random solution of the equations of motion. Sure, it has this tantalizing property that at infinity, it's minimizing the energy, since the energy is positive definite, and it's giving you that something that at infinity is 0. But this is quite not enough yet to conclude that this object is relevant to the ground state of the theory. To conclude that this is indeed the case, we have to start with solutions that are really pure gauge. So now I'm going to call my gauge field something like this. And so as we just said, this configuration minimizes the energy. And so at this point, we have to ask how many there are. So how many inequivalent solutions of the equations of motion that minimize the energy exist. Because if there is more than one, then the vacuum is not going to be trivial. It's going to be either, well, a specific one that we have to find, or if these objects are all degenerate, we have to ask if they can be connected to each other. So if you can transition from one to the other. If you can transition from one to the other, just like in quantum mechanics, where you tunnel, say, from the two minima of your potential well, the true vacuum state is going to be a superposition of all the generate vacua that you can find. So the first step is to answer the question of whether there's more than one of these configurations that is not equivalent. The second step is to verify that they all have the same energy, but it's kind of guaranteed already by this form. And the last step will be to show that this solution interpolates between these different vacua. So essentially incorporating these solutions in your path integral is selecting the correct QCD vacuum, okay? Just like when you symmetrize over the two minima of something like this in quantum mechanics, or you anti-symmetrize depending on the statistics of your particle. And so, okay, step one is counting how many inequivalent configurations exist. And I'm going to just sketch for you the argument. So first of all, we can fix a gauge, and I'm going to choose the temporal gauge. This choice guarantees that my remaining gauge freedom is time independent. Okay, so now I have to count all gauge transformations that depend only on the position in space. And the second thing that I have to do is to impose boundary conditions, and I'm going to choose the following one. So I want our gauge transformation to go to 1 when we are going at large distances. Well, so this is a boundary condition needed for our solution to make sense. But effectively, this choice is compactifying our space. So we started by looking at R cube. But now one can show that we are looking at S cube. Okay? I'm not going to prove this to you, so we're looking at a sphere. But if you think about it, this is not that different from the stereographic projection of the sphere by Riemann that you might have seen in some analysis courses. Because what we're saying essentially is that all points at infinity on this plane converge to the same point. So it's, if you remember, there is this ambiguity associated by the North Pole, which projects to all points at infinity. It's exactly the same. So this is kind of a very hand-wavy argument to tell you why this is the case. In reality, one can prove it. So with this, so in this gauge and with these boundary conditions, essentially we're looking for functions U that map the sphere to SU3 color. Okay. And counting how many inequivalent classes of these functions exist, it's an interesting exercise in topology that I'm not going to do for you. I'm just going to tell you the answer. The answer is that there are as many inequivalent maps as there are integers. So the mathematical notation for this is that this mapping to the 3 sphere, pi 3 of SU3, is equal to the integers. So what we're saying is that we have one of this solution for any integer. So we can label them with some index n. So this is this concludes, yes.
So again, how do you find equivalence between such mappings so you classify them? Which U's will be in the same class?
Yes, so what essentially I'm going to call two mappings equivalent if I can deform one into the other continuously. So those that are inequivalent are the topology classes. Okay. Today, yes, given the amount of stuff that we need to cover, I'm not going to be completely rigorous on everything. I'm just going to give you a flavor of how this works. But so if you want to understand better what's going on, well, Weinberg's book, Quantum Field Theory 2, is always fantastic, even if the notation is what it is. But otherwise, well, you can also try Coleman aspects of symmetry, although I don't know if it goes all the way down here, but at least it tells you more about instantons than I will. Or there is Schiffsman's book as well, so plenty of references to look at. All right, so essentially what we've done with this, well, essentially I've only sketched for you the logical steps, but what we've done, yes? It's taking us from S3 to SU3, so. Exactly, yes, yes. So no, I mean, U is an element of SU3, exactly. So if you consider U as a function of your space-time coordinates, right? So if you give U your space-time coordinates, which are an element of S3, U is giving you an element of SU3. Okay, so the mapping goes in the direction that I wrote on the blackboard. Let's see. So you are taking as input a space-time point, and you're getting as output an element of SU3. All right, so essentially this very unwavy derivation is showing you that there are many inequivalent vacua in QCD, labeled by these indices n. And one can show that this solution that I just written down is interpolating between them. More precisely, the expression that you have here, it's interpolating between two vacua that differ by 1 unit. So let's say if this is time, at time minus infinity, this instanton is in some vacuum, and at time plus infinity is going to end up into this other vacuum where the delta n between the two vacua is equal to 1. Okay, so this is very similar to a tunneling solution in quantum mechanics. Is essentially moving you from one vacuum to another one. And so this essentially is at the core of the reason why we have to consider these configurations in our QCD path integral. Because essentially only if we include them, we are looking at the correct vacuum, which is a superposition of all these different vacua labeled by n. And okay, you can check again with some pain that if you compute our famous GG dual term on these instanton configurations, you're going to find essentially delta n, so the difference between the n of the two vacua that they interpolate between. So in the case of this expression, you're going to find 1. And okay, the easiest thing to check is that indeed these solutions scale at infinity in such a way that k scales like 1 over r cubed, so does not decrease more slowly than 1 over r cubed. So on these instanton solutions, k is going to go like 1 over r cubed at infinity, and it's giving you this finite contribution to the action through GG dual. Sorry, I know that you guys don't like when I go back and forth between the blackboards, but I promise I won't do it again. Okay, so I would say that this almost concludes the most abstract part of the lecture. I just want to tell you one more thing, mostly without proof, but I'll give you some intuition, which is the following. So you might wonder how the vacuum depends on theta, right? Because now we've seen that there is a term in the action that's proportional to theta that knows in which vacuum you are, right? So it's at least it's sensitive to some parameter that is telling you in which vacuum you are. And in the end, so one can show that, but well, it's a pretty long calculation, that the actual vacuum of QCD looks like this. And okay, it might seem that I pulled this expression out of thin air, but I want to try to give you some intuition, at least for why theta is appearing as a phase, okay? There is the high risk that this might confuse you more than help you, but I think that there is always a benefit in seeing results in multiple ways. So you can find this result proven rigorously in all the books that I listed before. And now I'm just going to give you another end-wavy argument for how this comes about. So we're going to start with something relatively basic in quantum field theory. So you know that if you're looking at a transition probability like this one, you can write it as a path integral with some appropriate boundary conditions. So at t equals 0, the field is at phi 1. Yes, I didn't invert them. And at t equals delta t is at phi 2. But nothing stops us from defining a formal object, so a state, which if you want, it's the initial state evolved in time, as a path integral with an open boundary condition. So at early times, we have the same boundary condition as before. At late times, we don't specify any boundary condition. And this kind of abstract object is mostly used in applications of quantum gravity. But for our purposes, I want to say something much simpler, that if you think about the path integral in this way, then you can also think about wave functions in quantum field theory, right? So you could call this a wave function in the sense that you give it a field and it gives you a complex number. And given what we just written down, this wave function is just the initial path integral. So with the two boundary conditions that we had before. So you might wonder where the hell I'm getting at, but you will see it in a second. So okay, so now we have some sort of operational definition of a wave function in quantum field theory. But okay, the problem, the cross of all particle physicists remains, which is that essentially we know how to compute only one functional integral, which is the Gaussian one, so where everything is free. So if you have an interacting theory like UCD, okay, either you go to the lattice or there's not much you can do, except in the case where this phase is large in some sense. So when the action is much bigger than h slash. Okay, in that case, there is something more that we can do because let's expand the action around some value of the field. Okay, I'm not going to rewrite the boundary conditions because it just clutters the notation, but you have to assume that I'm always assuming some boundary conditions. So I can expand the action around some constant value, sorry, not constant, but some value of the field, okay? And what's the best point around which we want to expand our action? So the best point is the solution of the classical equations of motion. The reason is very simple, because on the classical equations of motion, this is 0. So essentially, if you want, this classical trajectory in field space that correspond to your classical theory is the one that is in the region that is the most flat, okay? So there is some region around this trajectory where the action is not changing much. And so all the quantum paths in this region are summing coherently in the path integral because the phase is remaining the same. And instead, all the other paths that are farther away are summing incoherently and roughly canceling each other out. So this is essentially just the classical limit of quantum field theory. And so you can always, making some mistake, approximate the path integral with just the first term. So the first term is evaluated on some fixed configuration of the field. So from the point of view of the integration over different configurations of the field, it's a constant, so you can bring it out. Then in practice, we're never dealing with the path integral, but always with the path integral divided by something that normalizes it. So the infinite number that you get by integrating 1 times the measure always goes away. So okay, we're going to have some infinite number here in front, but it's not going to give us anything physical. And so if you want to refine your approximation, so okay, around the classical equations of motion, this term will be 0. This guy will look like a Gaussian integral. So in principle, you can you know how to compute the first, the leading correction, but we're not going to do it. So for now, we're going to just look at the leading term, at least in this limit where h slash is small. And so, okay, what's the leading term? The leading term is the action evaluated over the classical solutions of the equation of motion. And so if we evaluate our action on an instanton solution, we're going to get a term that looks like theta times some difference of integers, right? So we're going to get that this term has a factor that looks like this. And so by comparing this result with what I told you a moment ago about the wave function, essentially we've seen that we expect theta to enter as a phase in the wave function of the vacuum, at least in this limit. And this is also telling you that in some sense theta is the conjugate variable to these ends. So if you think about, I don't know, a plane wave function, you would have e to the I momentum times r, so the product of the two conjugate variables. Yeah, so I don't know if this makes it more or less believable, but it's one way to get at least an approximate understanding of what's going on. Yes. This one? This is CL, sorry. So it's meant to be the classical, the solution of this equation. So the solution of the classical equation of motion. So for example, our instanton is the solution of the classical equation of motion that we care about in QCD. So it's the one that it's describing the right vacuum. Yes. Sorry, our theta. That's, well, okay, so this is all in the semi-classical limit, but the next thing I want to do is to show you that theta is a phase in a less sophisticated but much more convincing way. And I'll show it to you in a second. Before that, yes? This n. Yeah, so essentially, well, so if you think about, so in 3 dimensions, it's a bit complicated, but imagine that you want to map a circle to a U1, okay? So now you're just looking at a U1 transformation. So you're asking essentially, So U1 is itself a circle, right? Because any element of the group can be written like this, let's say, okay, e to the I sum phase. So you're asking in how many ways can I map a circle to another circle? And essentially, there are as many, so you can wrap it around once, or you can wrap it around twice, or 3 times, or 4 times. So essentially, also in this case, there are as many ways as there are integers to map one into the other. And essentially, this is the same. So it's telling you that you can write a gauge transformation that is mapping SU3 to the sphere by wrapping it around once, or 2 times, or 3 times, and you cannot deform one into the other. And this index n essentially is telling you how many times you are winding your SU3 around your sphere, sorry, your sphere around your SU3. And it turns out that this object, so this GG dual, it's a famous topological invariant that it's counting this number of windings. So when you do the integral, you get this n. So I know it's not much clearer than before, but this is what it is. Yeah. Yes. Yes. So well, essentially, it's just that each one of these. So you don't care about how U looks like here. If you can write a function like this is going to minimize your energy. So your field strength of the gluon evaluated on this expression formally. So if U is a gauge transformation, any gauge transformation is going to be 0. Okay. Now you found that you can have infinitely many of these gauge transformations that differ from each other by this winding number that respect the same boundary conditions at infinity. So each one of them is a different solution of your theory with the same energy. In some sense, well, maybe it's easier if you think about a scalar potential, okay? So let's say if you had a potential like this, you would have 2 different values of the scalar for which the energy is the same, okay? Here, you're doing the same for a vector. So you're asking, what does the potential of this vector look like? And we just found that there are many, many places where the potential has the same value. Each one differs by this n, okay? So let's see. So yes, so we were at wondering what this, so why this theta is a phase. Well, okay, a simpler way to see it from the low energy perspective is that if we write again the chiral Lagrangian as we did yesterday, then we are going to have these 2 terms. And if you remember yesterday, we had put theta into the quark mass matrix. Okay, but imagine now that you're setting to 0, say, this term. Okay, let's say that B is 0. If B is 0, you can always rotate U without touching anything else, and you eliminate theta from your theory. If A is 0, You cannot immediately conclude that there is no theta in this Lagrangian because of what we said yesterday. So if you remember, in the UV, you can move theta either in the quark mass matrix or in GG dual and back. Okay, so if the quark mass matrix is 0, you might still have a GG dual. So it's possible that now you have your phase in B or in U. But again, you can rotate U in the same way as before. And nothing else in your Lagrangian is going to change. So the kinetic term is invariant under this shift. So what we are seeing by this exercise is that you need both terms to be present for theta to have an observable effect. And the reason is that, well, if you want, this is another indirect proof that theta is a phase. Because you need, so each one of these terms independently is going to generate some matrix elements, okay? Some transition probabilities between different states, okay? So in principle, this can mediate some process. I'm going to call the matrix element M1, and this is going to mediate some other process M2, okay? If theta was a coupling like any other, well, clearly, so when we compute something physical like M1 squared, you would still have some contribution that looks like this, or like this. But what we're saying here is that we need both M1 and M2 to be non-zero to see theta. And the reason is that only the interference between the two is sensitive to theta. So this is telling us that theta is a phase because these two terms, where you square out the phases, are not sensitive to it. You get an observable effect only if two amplitudes that break the symmetries in the same way exist and can interfere. Okay, so I think we can, yes.
The matrix elements M1 and M2 squared cancel each other?
No. So you can still have some process that looks like M1 squared, but it's going to be insensitive to theta. So I shouldn't bar, okay. I should do this. So M1 squared, let's do this, okay? But this guy instead is dependent on theta.
Each of them is only in the limit of the other one vanishes, right?
Sorry?
The M1 is only 0 if B equals 0.
Yes, so M1 and M2 are essentially coming from taking the matrix elements of these two operators. So if, say, if B equals 0, M2 is 0. If A equals 0, M1 is 0. And so when you compute a physical process, if both matrix elements contribute, you're going to have this plus let me call it dagger to be more precise.
No, but it's only if both are non-zero, then you also have theta dependence in each of the square.
So no, so if both are non-zero, these two are still independent of theta, just because it's a phase. And the only dependence comes from these two terms. Okay, so this is not exactly a proof. Okay, this is just giving you another hint as of why theta is a phase. So essentially, you're finding that if you compute a physical process, you have a theta dependence only if two amplitudes that can interfere are both non-zero. So this is a strong indication that theta is a phase. Okay, so I think that we can consider this first part done. Now we're going to talk about the quality problem. So yesterday we wrote this coupling of the axion, and argued that it can explain why we observe such a small theta. And so we can ask where this is coming from. I'm going to write possibly the simplest model that can do this for you, which is known as KSBZ in the literature. So your Lagrangian will contain some scalar and some left-handed spinors. And the scalar has a Mexican knot potential. And I'm going to imagine that there is a U1 symmetry. I'm going to call PQ, under which the scalar has charge -2, and the two quarks, and the two fermions have charge 1. I'm also going to imagine that these fermions have some charge under SU3 color. So they transform in some representation, okay? And one is the conjugate representation of the other. So this is an R, even if it's not very clear. So if this is the case, then you can expand the scalar around its vacuum. Where rho and A are the two fields parameterizing the 2 degrees of freedom of the complex scalar. And then you can ask what happens at low energy. So let's say that we're at an energy that is much smaller than Fa, okay? And let me further imagine that the coupling of the quarks is order 1 for simplicity. So the mass of these quark-like objects is going to be of order Fa. And also the mass of this rho scalar is going to be of order Fa. I'm also going to assume that the quartic coupling of the scalar is of order 1. So to see what happens at that energy much below Fa, you have to integrate out the radial component of the scalar and the quarks. And one can show that at one loop, you're going to generate our GG dual coupling. So there are these quarks in the loop. And this is going to give you a coupling at low energy that looks like this. With some coefficient A, which is known as the anomaly coefficient, which is proportional to the trace of the U1 generator times 2 SU3 generators. So if you want, we can put color indices on GG dual and on the anomaly. Okay, so you can see from the charge assignments that this coefficient is not going to 0. You can also see from the loop where the coefficient is coming from, because here you have a PQ generator, and here you have 2 color generators, because we are looking at gluons coming out. And, well, this is the result of the calculation. You could have guessed it from CP invariance. If you assume that all couplings are real, then the scalar, if phi was CP, then the scalar is CP odd. And so the only CP conserving term that you can write at low energy is this one, because under CP, both A and GG dual go to minus themselves. So if at low energy you have only gluons and this axial particle that does not get a mass from this potential, then this is the only term that you can generate. So you can guess it even before writing down the loop. You can guess it in this way, or you can even guess it from the PQ symmetry itself, because here we used a slightly different notation compared to yesterday. So we wrote both Q's to be left-handed spinors. But if you map this simple model into the Dirac notation that we were using yesterday, which I encourage you to do as an exercise, you're going to find that this U1 PQ is the axial U1 that we've been talking about. So under this axial U1, GG dual is shifting, and also the axion is shifting, right? So if you do a phase transformation on the scalar, the axion is transforming non-linearly. So it's going to A plus a constant. And so also from these symmetry properties, in principle, you can deduce how the theory is going to look like at low energy. This is done in more detail in the chapter on anomalies of Weinberg's quantum field theory 2 books. And it's an illuminating read if you want to do it. But OK, this explicit construction, more than to tell you where the GG dual coupling was coming from, is here on the blackboard to show you a potential problem with this axion idea. Because now, OK, now you have a UV complete theory. So you know that above the scale FA, you have to write your theory in a PQ invariant way in terms of this scalar phi that has definite transformation properties. But in principle, OK, there is no reason why quantum gravity should respect this symmetry. We have some hints that it doesn't like global symmetries. So we might have operators that look like this, where I'm implicitly assuming that n is bigger than 4. And what happens if we have operators that look like this at high energy? Well, we can simply substitute the solution the parametrization in terms of the axion that we have here. And we're going to find that these operators give you a potential to the axion. And potentially there might be a phase if, for example, there is some coefficient in front which is not real. And so now this potential is competing with the one that we computed yesterday from QCD. So at very, very low energies, so if we go even below the QCD scale, our axion is going to have this contribution of this to its potential, but also a QCD contribution that looks like the one we wrote down yesterday. Okay, that now I'm expanding to simplify our lives. So you see that there are two competing terms. So this term wants the axion to cancel theta bar, but this term wants the axion to cancel another phase that has nothing to do with the neutron EDM. So if this contribution wins, it pulls us in a vacuum where the neutron EDM is again big. And so for the solution that we proposed yesterday to work, we need the second contribution of the potential coming from high energy to be very small. So in practice, we want this object to be roughly 10 to the minus 10 of the QCD contribution. And yes? What's in the argument of the first cosine? Yes, so I'm imagining that these operators are generated with some coefficients that are complex. So it's the phase of the coefficient in front, essentially. And OK, you get an n in front of the axion because it's phi to the n. So but literally, I'm just plugging this expression in here, and then using the Hermitian conjugate to get a cosine. So here I'm going to have e to the I n axion plus e to the I phi, e to the I n axion plus phi n, and here I'm going to have minus. No problem. So yeah, so I need this to hold, and if I want to be consistent with the experimental bound that we wrote down yesterday, in practice this means that if I consider the smallest FA consistent with experiment, which is around 10 to the 8, 10 to the 9 GeV, then I need n to be bigger than 14. So essentially, we're saying that this operator don't exist up to an insanely high number, n. And so, okay, this is telling you that in some sense, you have pushed the problem of explaining why theta is small into a problem of engineering a high energy theory that aligns very precisely with QCD, so it doesn't have any of these terms in it. And this is known as the axion quality problem. And there are many proposals for its solution. But so, as it's the case always in life, especially if you're a theoretical physicist, you start with something simple and beautiful, like adding 1 degree of freedom to your low energy theory, and you end up with something extremely involved. So essentially, well, you're paying a price. I mean, and it's not surprising. I mean, as far as I know, nature doesn't give us anything for free, and explaining a small number, it's not that easy. So, okay, we are incredibly doing relatively well on time, so we have done point 2. Yes.
If I remember correctly, there's also somehow the effect by 7 loops or so. This is also something at this smaller number.
You mean in the standard model? Yes, indeed. So in the standard model, if I remember correctly, there is a finite contribution at 6 or 7 loops, and then a UV sensitive contribution at 8 or 9 loops. I forgot exactly. But they all have so the reason why it's at this high loop order is that to write down the CP violating invariant in the standard model, you have to go through all elements of the CKM matrix, essentially, to build up the Yarskog invariant. So you have all these loops that look like a W, and then another W, and another W, and so on, until you get all the CKM elements, and you get something that is physically sensitive to the phase in the CKM matrix. But it's compared to 10 to the minus 10, this number is tiny, even if you take the UV sensitive part to be a 10 Planck. So I don't remember the exact number, but I vaguely remember that it's in the ballpark of 10 to the minus 24, but I might be wrong. It might be even smaller. Yeah. Yes?
The quality problem is really telling us that we can't have any effective interaction of phi fields with lower than phi to the 14th.
Yeah, well, if you want, it's even worse, because these are gravitational interactions. So if you have an interaction that is suppressed by a smaller scale than m Planck, this number becomes even bigger. Yeah. All right, so let's get to topic number 3. So the axion doesn't necessarily have to solve the strong CP problem. It might, but it's also an interesting dark matter candidate, even independently of the story I told you in the last 2 lectures. And it can be a dark matter candidate in the same sense as the scalar that we've seen at the end of the 2nd lecture. So let me imagine that the potential of the axion is dominated by QCD. Okay? Then I can expand the exact result I wrote down yesterday, or the approximate result that I wrote down today, and I'm going to find terms that look like this. So I'm going to find something like lambda QCD to the 4th, and I'm telling you in a second what I'm calling lambda QCD to the 4th. Where FA squared times A squared times some number plus lambda QCD to the 4th over FA to the 4th, A to the 4th, and so on, okay? But the more I go on, the more powers of 1 over FA I have. And given that the experimental bound on FA is pretty big, effectively, in most of what I do, at least at leading order, I can ignore the interactions of the axions. So this quartic coupling is really tiny. It's 100 MeV over 10 to the 9 GeV to the 4. So effectively, this axion is a free field, just like the scalar that we talked about on the first day, with this mass that I called lambda QCD to the 4th over FA squared. And for me, okay, so if you want to be a bit more precise, for me, lambda QCD, well, let me define lambda QCD squared is m pi squared, f pi squared, where m pi is that of the neutral pion, and down, up plus and down squared. Sorry, no, this is lambda QCD to the 4th, never mind. And this is roughly, so 80 MeV to the 4th, okay? So there are many, okay, this is not the traditional lambda QCD, okay? So this is, I'm going to call this quantity lambda QCD because it's very convenient for the axion. So this is my personal definition of lambda QCD, which is around this number in the standard model. So, okay, now in principle you might think, I have a free scalar, I just redo the exact same that I did for our free scalar in the second lecture, and I get dark matter. However, the axion is a bit more complicated because at high temperatures, the QCD coupling is small. So this QCD scale effectively is 0. So early in the history of the universe, the axion has no potential. In practice, you can parameterize this effect by the fact that the axion has some temperature-dependent mass. Okay, the quantity that people usually define in the literature is the topological susceptibility, which is defined as the mass squared times FA squared. So you will find, if you look in the literature, plenty of calculations of this number. For our purposes, we're going to use a very rough approximation, which is the following. So when T is much bigger than a GeV, we're going to say that the axion mass scales roughly like lambda QCD at 0 temperature, so this number here, divided by the temperature to the power of 4. Okay, so I don't know why these blackboards become so smooth on the side. Whatever you write is invisible, but I hope you can see this. So it's just lambda QCD over temperature to the 4th. So the mass essentially is turning on very rapidly, like 1 over T to the 4th as the universe cools down. So the picture compared to our free scalar is slightly different. So at very high temperatures, the axion has no potential. So then it starts turning on say when the temperature is close to lambda QCD, it starts turning on, as we said, like 1 over T to the 4th. And then, just immediately after the QCD phase transition scale, so this lambda QCD, well, let me call it tilde, is not exactly the same that I'm using for the axion, but it's the one relevant for the phase transition. So when the temperature is smaller than this scale, then the potential is turned on. And so here you see that you even have kind of a good excuse to say that the axion, you expect the axion to be misaligned from the minimum, right? Because at very early times, at high energy, there is no axion potential. So the axion could be anywhere. In general, so just based on dimensional analysis, you expect this misalignment that I'm going to call, well, let me call it A bar, purely from dimensional analysis, you expect it to be of order FA, because this is the typical scale of the potential. So if you take derivatives of this potential, you'll see that the scale over which the potential changes at order 1 is FA, okay? Well, actually, you see it immediately when you do this expansion, because you see 2 derivatives, 1 over FA squared. 4 derivatives, 1 over FA to the 4th. So the most natural expectation, if you know nothing about the UV, is this. And now, okay, we just repeat what we did last time. So we solve the classical equation of motion. Only this time, the mass depends on temperature. And the reason why, okay, we are in this regime of light dark matter particles where we can have a classical description is what we said before, right? So the mass of the axion is roughly lambda QC to the 4th over FA squared. But FA squared is at least 10 to the 8, 10 to the 9 GeV. Lambda QCD is this 80 MeV number here. And so you see that if you put the numbers, you'll see that we are in this classical regime. And OK, we've seen how it works for this equation last time. So if you plot the value of the axion field, say, divided by FA as a function of the time, so 1 over the temperature, initially it's going to be stuck. Then at some point, Hubble becomes comparable to the mass. And then the field starts oscillating with an envelope that redshifts like cold dark matter. So the amplitude of the field goes down like 1 over the scale factor to the 3/2, so that the energy density, which is this amplitude proportional to this amplitude squared, goes down like 1 over a cube. Okay? So if you repeat the exact same calculation that we did last time, we're going to find that the axion relic density today divided by the dark matter relic density today is going to be the mass when oscillations start times this misalignment. And let me parameterize this misalignment as FA times a theta 0, okay? This essentially is factoring out the natural estimate and is leaving you a dimensionless parameter to tell you how close you are to the natural estimate. So you have FA squared times theta 0 squared divided by, okay, our usual, our favorite parametrics. So 1 electron volt times the oscillation, the temperature at which oscillations start, cube. The reason is that this object starts redshifting like dark matter at this time. Okay, so if we redshift it until today, we're gonna get just a factor of T0 upstairs, T0 downstairs. So in the end, the only moment that matters is when oscillations start, because at that point, this energy density is going to start decreasing in the same way as the dark matter energy density. OK, so, well, we can get this oscillation time in the usual way, approximating Hubble with T squared over m Planck, and equating it to the mass. And so we're going to get something like the following. So this is an m Planck to the 3/2. This is an ma to the 3/2 that we got from this equation. OK, so now the only difference compared to what we already did is that we have 2 regimes. So this oscillation temperature can be bigger than lambda QCD. So we have to use the temperature-dependent mass which is going to be the 0 temperature one times our scaling that we wrote down before, to solve for this equation, so to get it equal to Hubble. Because, well, the mass is still temperature dependent at high temperatures, and if we do that, we're going to get a T oscillation that looks like lambda QCD to the 2/3 times m Planck to the 1/6 times axion mass at 0 temperature to the 1/6. And so this scales roughly like 1 over FA to the 1/6. And if we plug this back into the equation for the relic density, we're going to get that rho axion over rho dark matter today is roughly the axion mass to the 1/2 when oscillations start, right? Now I'm just taking the ratio between numerator and the denominator, times FA squared times T0 squared. So this is how it scales. So this is how it scales with the axion parameters. If you put all the numbers, then you're going to get something like 2 times 10 to the 4 times FA over 10 to the 16 GeV to the 7/6 times theta 0 squared. Now we have also a second regime where this T oscillation is smaller than lambda QCD. At this point, we can just use the 0 temperature mass, and we're going to get the same result that we got yesterday, sorry, 2 days ago for the scalar. So in this case, well, again, if you plug everything in this ratio, you're going to get that it roughly scales like FA to the 3/2. And if you put the numbers in practice, you're going to get 5 times 10 to the 3 times FA over 10 to the 16 to the 3/2 times theta 0 squared. Okay? So if we imagine that theta 0 is order 1, so our natural estimate is realized, then we're going to get that to get the right amount of dark matter, in both cases you need FA close to 10 to the 12. I put here 10 to the 16 GeV because it's a more appealing number from the point of view of UV complete model. So for example, for axions coming from string theory. But the FA that gives you dark matter is roughly around 10 to the 12 GeV. Okay? The question remains, however, exactly, how to get, where theta is coming from. Well, so first maybe let me say that this 10 to the 12 GeV corresponds to an axion mass of order 10 to the minus 6 electron volt. Okay, so these are the magic numbers for the most vanilla possible axion dark matter. Of course, the moment you take a step beyond these very simple models, essentially you can have axion dark matter everywhere in the FA-MA plane, even beyond the QCD line, right? So if you were to plot, let me do it here. So if you were to draw a plot of the axion mass versus its couplings that scale like 1 over FA, the model that we just described, it's a line, again, in this log space. But, well, okay, there is a whole literature in how to move around in this plane away from the line, and now you can get dark matter essentially everywhere. But, of course, this required some more work compared to what we did today. So before concluding the dark matter part, let me just mention one aspect of our discussion of theta. So if FA is bigger than Hubble during inflation, then you can imagine, okay, that the universe started with many different values of theta. So in some place, theta theta, when I say theta, I mean the misalignment in this discussion, okay? So theta 0. So theta 0 can have some value here, can have some different value here, and so on. But if FA is bigger than Hubble during inflation, the axion already existed during inflation. So in practice, what we're seeing is a single patch that it's inflating until today. So we expect theta to have the same value everywhere in our universe. And our simple calculation of the relic density is not so far off the mark. However, if we imagine that we are in the opposite situation, so that the axion doesn't exist during inflation, then in principle we can have, well, within our universe, many different values of theta. And these could be separated, these are separated by strings and domain walls. And this lower dimensional object contains some energy. And one can show that when Hubble becomes comparable to the axion mass, these objects decay, okay? And they decay into axions. And they give a non-perturbative contribution to its relic density that scales like some positive power of FA. And the exact value of this energy density is still the subject of active research. So there are groups that are currently disagreeing. But if this is the case, that prediction might not dominate the axion energy density. It might actually be these non-perturbative effects which dominates it and predicts a slightly heavier mass, around, I think, 10 to the minus 5, 10 to the minus 4 EeV. But as I said, this is still the subject of active discussion. In principle, you can also produce these particles thermally. So for example, we've seen yesterday that this object mixes with the pion. So we're going to have processes like this, for example, below the QCD scale. But, well, I leave you as an exercise the calculation of the relic density from these processes. And you will see that if the axion is lighter than 1 electron volt, these are negligible. So this, if you want, there are 3 ways to produce these axions. These strings, misalignment, and thermal. Thermal gives a negligible contribution for masses. So let me write it negligible for MA smaller than an electron volt, roughly. Misalignment, in principle, it's always there, but it might be dominated by strings if the symmetry is broken after inflation. Other than the coupling to GG dual, in principle, the axion can have other derivative couplings to the standard model. Okay? So the simple UV model that I've written down is not the only option. And in many cases, you generate a bunch of other couplings. In practice, you can write down everything which is consistent with the symmetries, and you can easily find models that realize it. Rather than writing down the full axion effective Lagrangian, just to make the connection with the next part, which is going to be very short, I want to say that you generically expect also an axion coupling that looks like this. Times some number, where F is the photon field strength, okay? And you expect this even in models, in the models that we just discussed. So even if you have only the axion GG dual coupling, the mixing with the pion will give it a coupling that looks like this, with C roughly 4 times 1.29, okay? Just the fact that the coupling to GG dual mixes the axion with the pion, and the fact that there is an electromagnetic anomaly, there is another global symmetry anomaly with respect to electromagnetism, gives you this coupling at low energy. So even if you don't generate it at high energy. If you want to know more about the calculations of the axion that we've seen today, some good references would be these two. So Axion dark matter and also the Axion potential from QCD. And these are, yeah, I mean, they have some focus on computing stuff. So they are more precise than what I told you. And if you want to know where this number is coming from, it's really just a ratio of quark masses. So it's roughly minus 2/3 for MD plus MU over MD plus MU. So this whole object. Okay, so this part I think was much clearer, but you could tell that I'm getting tired or I'm less excited about it, so we went a bit more slowly. And now we are left with the last part of the story. So we just have 10 minutes, so I'm not going to be able to tell you everything, but it's nice to make some contact with experiments. So these days, many of us are starting to think about new experimental proposals. So it's becoming also a theorist business to understand how experiments work. Mostly because in some cases, well, you need a non-trivial amount of theory to propose these ideas. Indeed, traditionally, okay, probably the most famous axion dark matter experiment, ADMX, was proposed by a theorist, by Pierre Tsikiri. So what did we learn about axion dark matter from the point of view of experiment? So we learned that if we are in the most predictive case, so where PQ symmetry is broken before inflation and misalignment dominates the dark matter production, the axion looks roughly like a classical field. And its amplitude is proportional to the dark matter energy density today. Okay, this relation can be easily found if you compute the averaged energy density as we did for the scalar. But even if this is the explicit result of this misalignment calculation, in reality it's more general than that, because no matter how the axion is produced, if it's light enough, today and also throughout the history of the universe, we're going to have a huge number of axions in a de Broglie volume for the argument that we saw for the scalar. This means that this classical field description is valid no matter how the axion is produced. Okay? The only subtlety is how axions cluster in the galaxy. Okay? So writing it down as a monochromatic cosine is assuming implicitly that small velocity dispersion that we were talking about a few lectures ago. Because if the axion has a small velocity dispersion and it's non relativistic in the galaxy, then, well, its kinetic energy is going to be much smaller than the mass, first of all. And also its momentum, it's going to be much smaller than the mass. And so, okay, when we write this classical field, we can approximate the energy with the mass, and we can neglect spatial dependence, okay? Because over scales that are much bigger than 1 over ma, this field is not changing, okay? So the typical length scale over which this description holds is 10 to the 3 over the mass. And the typical time scale over this description, over which this description holds, is 10 to the 6 over the mass. Okay, so for 10 to the 6 oscillation cycles, this object really looks like this monochromatic cosine. If you want to be precise, in reality, okay, you have to add a more complicated function. So you're going to have also terms that oscillate at this much smaller frequency. And you're also going to have some spatial dependence. But if you're building an experiment on a length scale smaller than this, and you're looking at your axion for a time scale shorter than this, you can neglect these small corrections. The exceptions to these simple pictures do not come in the description as a classical field, but they come in the coherence property or properties of this field. So it's possible that this axion has a different profile in the galaxy that we naively expect from the misalignment mechanism. And this in particular can happen in those cases where PQ symmetry is broken after inflation, and you can have regions of the universe with different values of the misalignment angle. But if we stick with this description, we are looking at a very monochromatic field. So the natural thing to do is to ask if we know how to manipulate other classical fields, and we know how to make them monochromatic, to see if we have any chance to see it. And indeed, well, electromagnetic fields are the prime example of what we know how to manipulate well in the lab with a large amplitude and a very small frequency spread. So the first thing that you want to do is to look at the coupling of the axion to electromagnetism that, as I told you a few minutes ago, you expect to have on general grounds. So even if it's not generated in the UV, if your axion is coupled to the gluons, it's also going to be coupled to the photons through the mixing with the pion. And if you write this object in terms of electromagnetic fields, you're going to find the following result. Okay, so, well, in less than 5 minutes, I'm not going to be able to tell you much more than this, except that, well, let's say the standard idea is that you turn on a magnetic field in the background, and then the axion is mixing with the photon. So in practice, you're turning on some magnetic field, the axion is coming in, and in this field, it can mix with the photon and give you an observable signal. Okay? I leave you as an exercise to compute, to estimate this coupling that, as we said, is of order alpha over 2 pi times 1 over fa in the case of the magic numbers down there. So for fa 10 to the 12 and ma 10 to the minus 6. And this will give you an idea of how hard it is to see this axion. So if you want to have a better idea, you can remember that in natural units, 1 Tesla is 60 electron volts squared. Okay? So if you compare these couplings with the largest fields that we can build in the laboratory, you will understand why it's extremely challenging to look for these particles. But so if I have to describe all experimental ideas to look for the axion coupling to electromagnetism in 30 seconds, here it is. So it's a box whose size is the inverse of the axion mass, because a box, so a conductor or a superconductor, is breaking translational invariance for the photon. This means that the photon gets a mass of order 1 over the size of the box. Or, if you want, in a more classical way to put it, you can expand the electromagnetic fields in the box into normal modes that resonate at frequencies comparable to 1 over the size of the box. Okay? Then you turn on a background magnetic field, and you look for a resonance signal building up. So if you match the photon mass to the axion mass, then you can build resonantly your signal. And if this box is a good box, so it has very little dissipation in its walls, then you can build a signal that is Q times larger than than you would have without this resonance, where Q is the quality factor of your resonator, which is essentially telling you how much energy you lose in the walls at each oscillation cycle. And for superconducting cavities, this Q gets to 10 to the 12. For normal conducting, to 10 to the 5, 10 to the 6. And this is the old business. So there are, of course, some variations over this idea, but they are all variations in disguise, okay? I'll tell you why. So if you want to, let's say you want to make the axion, so let's look at the magic numbers. So for the magic numbers, a microelectron volt is a few tenths of centimeters. So the box is the perfect size. You build it on your table, something that humans can manage well, okay? And indeed, our best electronics, best quality factors are all for these boxes of a few tenths of centimeters in size. Now, if you go at smaller masses, you need to build bigger and bigger boxes, and very soon it becomes impossible. So you cannot build a box that is a factor of 10 bigger than a few tenths of centimeters with these quality factors. You cannot put it in a fridge to cool it down and reduce the background. You cannot do anything. So at low energy, you cannot build a box, but you can still build a resonator. So the main idea is exactly the same. The only difference is that your resonator might be an LC circuit, so that the frequency doesn't depend on the size, but on other parameters that you can control. At high energy, you have the opposite problem, because the total signal will depend on the volume of the box. So of course, you can build a smaller and smaller box and still control it finely, at least up to some point. But you're losing a lot because you are trading your macroscopic volume for a tiny volume. And so the trick going at large axion masses is to replace the vacuum with some other material, because the resonant frequency is not really 1 over L, right? It is only natural units. It's really the speed of propagation of your electromagnetic field divided by the size. So if you have a material that is not the vacuum, here you can keep the size fixed, but change your material properties and get still the resonance that you want. So, and this idea, if you want, is also extrapolated to its fullest baroqueness when you think about a condensed matter system that can have exotic resonances with the photon. But effectively, you can map all these ideas into a box or a resonator. The only small exception is heterodyne detection, where instead of turning on a static magnetic field, you turn on an oscillating magnetic field, and this changes the parametrics of your signal, but okay. I'm already over time. To conclude, well, I had fun giving these dark matter lectures, but, well, I'm going to say something that probably is going to get me kicked out of particle physics if people watch the recording. But I have to say that dark matter is far from being my favorite problem. So I was a bit sad that Gilad stole the hierarchy problem lectures. The reason, okay, you see the reason in these lectures, right? So there is a lot of interesting physics in it. It's a very concrete problem that obviously we want to know how to answer. But there are perfectly good answers that are kind of boring. So, okay, if I find that dark matter is a WIMP or it's a completely decoupled scalar, I might have learned nothing deep about quantum field theory, nothing deep about the fundamental fabric of reality, what happens at very high energy. Okay? Instead, there are problems that are much less easy to describe, so they're not just an observational fact, but at the same time force you to think about the UV. So you cannot even start defining fine-tuning problems like the strong CP problem that we talked about, the Higgs boson mass problem that Gilad talked about, or the cosmological constant problem that I guess no one talked about, without thinking about stuff that for the moment we have not even imagined, okay? They really force you to think about the UV. You cannot even state the problem without making an implicit assumption on what's going on at energy so high that you don't even know if your quantum field theory works. So I'm sorry, but I'm closing up these lectures on light and bright particles. Well, technically, they were not lectures on dark matter, so it's fair to finish them this way. So I'm finishing them by telling you that, well, I enjoy a lot different problems, but the important take-home message from this last rant is that you should really ask yourselves, why are you working on a problem, okay? You don't have to take our words for it. If I spend 3 hours telling you about dark matter, it doesn't automatically make it an interesting problem for you, or I mean, it could be for some of us and not for some other of us. So anyway, so I think I've compromised myself enough in these last 5 minutes. And yeah, I'm sorry I didn't have time to show you the parametrics of light particles for the hierarchy problem, but those are very interesting. So there is a fundamental connection between light weakly coupled particles and the hierarchy problem. You partially have seen it with Gilad, but there is also a general power counting argument that, well, if you want, I'll tell you where you can find it, but enough. So I've already gone too far. So I hope you enjoyed it as much as me.
Questions?
So for this post-inflationary scenario of axion production, is there any hope of detecting a gravitational wave signal from the string decay or domain wall decay in the near future?
It depends what you call the near future. Let me think for a second, because so it depends. So the higher, well, there is some hope if we build LISA and possibly more advanced detectors. So I'm going to leave it at that. But the parametrics are that the higher the scale where, well, so what you really maybe have more hope of finding is if the PQ phase transition is first order. But there, so the higher the scale of the transition, the higher the frequency of where, I mean, you expect most of gravitational waves today. And it's extremely hard to see high-frequency gravitational waves, much harder than low-frequency ones. So, but at the same time, okay, this phase transition just gives you an upper bound on the maximal frequency. So you're going to have a tail of the spectrum also at low frequency. To be honest, I'm not an expert enough to give you precise numbers. The short answer is I think that if LISA and their future and future upgrades or future other gravity detectors go online, then I think we have some hope, at least maybe for the PQ phase transition. I'm not sure about the domain walls. If not, at the moment, not really, as far as I can tell. Maybe someone has a better answer. Maybe Felix has a better answer.
I don't know. Yeah.
So I actually have 2 questions. First of all, can you maybe give me a bit more of a physical picture of the instanton? So right now in my head, it's some very strange curly gauge field configuration that pushes me from one vacuum to another, but can I search for it at colliders? Will it show up somehow? Yes. And the second question is, nothing that we have done in the derivation was special for SU3, so it should also happen in SU2. So why is no one speaking about weak instantons and those stuff?
Yes, so let me answer the second one first, because it's faster. So the second one, the answer to the second one is that the symmetry that it's anomalous under SU2 left, so the U1 in the standard model that's anomalous under SU2 left is B plus L. this means that in the standard model Lagrangian, there is no explicit extra breaking of this symmetry. So if you write down something like this, where trace is just a sum over the SU2 indices, then you can rotate away this theta with a B plus L rotation, and there will be no physical effect. So purely within the standard model, this is what goes on. But we expect all sorts of B plus L violation, for example, from GATS. So you can have, say, this operator. And then this effect might be physical. And, well, Csaba and I are still trying, I'm sure that someone has done it, but Csaba and I are still confused because we want to use this, again, to solve the hierarchy problem. And we can't decide whether these instantons interfering with this explicit B plus L breaking give you something super tiny or something that might have some hope of being detected. But so naively, the biggest that these things can be, which I'm not yet convinced it's possible for them to be this big, is m gat to the 4 times c to the minus pi alpha at m gat, 2 pi, sorry, alpha 2 at m gat. So in principle, so if they are this big, they could do something, but okay, this is some UV sensitivity that is still confusing. I mean, okay, the short answer is just that in the standard model, this object is not observable, okay? If you go beyond, then the result becomes model dependent. And so you have to work it out, and it might be interesting for something, but it's also entirely possible that there is no B plus L violation beyond the standard model, and it would be surprising, but it's possible, and these objects have no effect. The first question, yeah, so the intuition I can give you is that you can represent the instanton as a effective operator, so as an effective vertex where all the fermions charged under both the gauge symmetry and the anomalous symmetry are coming out, okay? So for example, in the case of the QCD instanton, you would have all the quarks, and you have to repeat for the 3 flavors, okay? So you can think about the instanton as this effective operator that's very, very high dimensional with all these objects coming out. So if at the LHC you can see R vertex from which many particles come out consistent with these symmetries, so you could say that you've seen an instanton, but this is mostly relevant to models where they make SU2 run strong at energies of order the LHC. They add some B plus L violation, and there you expect some SU2 type instanton configuration. In QCD, okay, their effect, you're already seeing it through the mass of the eta and these other low energy predictions. The problem is that, okay, in QCD, these are not really, so these are not really free particles in some sense. So you're not going to see something like this. But okay, why you can write the instanton as this effective operator, it's a whole other set of lectures. So the original paper is the one by Toft, and then you can go from there. Yes.
If I may ask, now I got a bit confused by this last explanation, because you say it's like an effective operator, so it should appear at high energy, right? If I'm not mixing it up, or is it opposite?
Well, so this operator, yes, but the scale is dominated by. So the typical scale of this operator is dominated by low energy because. So if you remember, these instantons are classical solutions to the equations of motion. So when you do our, say, semi-classical approximation as we did before, let's say you write the Lagrangian. So if you write the Lagrangian like this, your instanton has no 1 over g star in front. If you write your Lagrangian with the usual normalization, the instanton solution looks like this, as I wrote it before on the blackboard, unless I forgot it, which I shouldn't have. So this means that, essentially all transition probability amplitudes, so all physical processes involving instantons, are going to scale like 1 over g coupling squared, okay? So this is also a way to show you that this is a non-perturbative effect, which is diverging when the coupling goes to 0. However, if you remember, the solution had a free parameter, this rho. So when you are asking how the instanton contributes to a physical process, you have to sum over rho. So there are some factors that get your dimensions right depending on what you're computing, some order 1 numbers. But OK, the main point is that this object is exponentially dominated by regions where the coupling is as large as possible. So essentially by lambda QCD. So whatever scale you have in your problem is going to be proportional mostly to lambda QCD. There is a contribution also from the X-VEV because, so to interfere with this, we said before that if you want a physical effect of what's in front of GG dual, you need to interfere two amplitudes. And so in QCD, we've seen that it's the quark masses and the instanton. So the instanton is dominated at lambda QCD. So when you close these loops, putting the Yukawas, so the quark masses in there, these loops are dominated by lambda QCD. And then you have these X's coming out. So you could close also the X loop, but then it would have this guy that forces you to be at lambda QCD. But you have also another option. You can put the X to its VEB. And since the X-VEB is bigger than lambda QCD, this is dominating over closing all the loops. And actually, this is interesting because it's telling you that, so an interesting fact that I didn't have time to talk about is that GG dual is the only operator in the standard model whose VEB depends on the X-VEB. No other operator has this property. So essentially, there is no local object that you can write in the standard model that depends on the X-VEB except for this operator. And it's a total coincidence because you need the X-VEB to be bigger than lambda QCD. You need a source of U1A breaking that can interfere with the instanton, so the quark masses. You didn't necessarily, OK, who said that the standard model needed to have exactly the right quark masses to close all these loops? One mass could have been 0, and this process could have been 0. And then you need the X-VEB to appear somewhere, so either in the explicit U1A breaking or in the instanton U1A breaking. And it's appearing in both in the standard model, both in the quark masses, but also in the running of G star. And I find this extremely fascinating because this object, which is the only local object in the standard model that depends on the X-VEB, depends also on theta, so the other particle physics parameter that we don't understand. OK. And OK, maybe I'm seeing too much into it, but you might think that the standard model is telling us something. And indeed, I know at least one example where you can solve both problems at the same time using this fact.
I mean, anyway, the point is that this operator gets no contribution above the confinement scale, right? It's all
no,
below.
It does, but it's very suppressed compared to the one below.
Mm-hmm. OK, thank you.
It's a quick and very naive question. You said about the dark matter problem that could not lead us to more fundamental answers, right? But I was thinking, like, if we get a new information about the detection of dark matter, could this lead us to new fundamental answers? Like, I was wondering about that.
No, for sure. So first of all, you should ignore everything I said at the end. And also because I contradict it actively with my work. So I spend, say, 30% of my time working on dark matter. So indeed, I think that there is a order 1 chance that dark matter will tell us something fundamental about nature, but we don't know a priori. So at this moment, we are confused. So my personal approach is to, well, start from important questions and see where these questions lead us experimentally. But at the same time, I want to hedge my bets. So I'm also thinking about what experiments can we build that teach us as much as possible about, well, the particles we care about. So indeed, I mean, in the end, you should ignore everything I said before. That's the short answer.
Okay, so let's close it there and thank Raffaele for his lectures. And for a closing word, I think on behalf of Rogério, Gustavo, Matthias, and I, we would like to thank, of course, the lecturers, but then, of course, all of you for making this such an excellent summer school. And the only, yes.
Thank also all the organizers, Felix, Rogério, Gustavo.
The only administrative note is that you should receive an email asking you to evaluate the school